Welcome to section 5.2. This section is on what's known as the mean value theorem. This is our third of our big theorems. So first there was the IVT, the intermediate value theorem, which said if a function is continuous on a closed interval, then we must hit all of the y values between the endpoints. The second was the EVT, the extreme value theorem, which said if a function is continuous on a closed interval, then there must be an absolute maximum and there must be an absolute minimum. And then we have the mean value theorem, or MVT. This is also an existence theorem, like the IVT and EVT. It just tells us whether something must exist. And it has a slightly different beginning to our hypothesis here, in that it says not only does f have to be continuous on a closed interval, it must also be differentiable on an open interval. So we need both of those before we're allowed to use the MVT. This is an extremely powerful theorem that is used very, very frequently. It has a lot of applications. But if a function is continuous on the closed interval and differentiable on the open, then somewhere in between a and b there's a value c where the derivative there would equal the slope of the secant there. So in terms of all the other names we have for these things, some people memorize this as f prime of c equals f of b minus f of a over b minus a. I usually think of it as the slope of the tangent, which I know is the derivative, equals the slope of the secant. Other people remember it as instantaneous rate of change is equal to average rate of change. And graphically what this is saying is if this is our function f here, somewhere, if I were to look and see what is the slope of my secant here, so if I draw a secant between my endpoints, somewhere there has to be at least one x value where the slope of the tangent is going to be equal to that. So if I look at it, it looks like right around here, this would be a c value where my slope would be equal to the slope of the tangent. Now there could be more than one, so like in this sketch, it looks like right here is another place where I could also have a c value, where the slope of the tangent is equal to the slope of the secant. Now, first thing to practice with this is just knowing when are we allowed to use it. So if I look at this graph, the first one here, it is continuous on the closed interval, a to b. However, we have a corner right in the middle of it, so it's not differentiable on our open interval from a to b. So we cannot use the MVT. Now this doesn't mean that there couldn't be some point where f prime of c would equal f of b minus f of a over b minus a. It just means it's not guaranteed to exist. If I look at the second graph here, well, the problem here is it is differentiable on my open interval, a to b, but it's not continuous on the closed because it doesn't include a. So again, no MVT. Third example could be something like this. It is continuous on the open or on the closed interval, a to b. And I do see a corner here, however, the corner is on A, and that doesn't affect the fact then that it is differentiable on the open interval from A to B. So you do have to pay attention that for differentiability, the endpoints aren't included in that. So I can use the MVT. And especially when you're using the MVT, you do have to make sure that the hypothesis fits. So a couple ways that they could ask questions about this. First would be, here's a function on a closed interval. Is that find a place, if it exists, where f prime of c is equal to f of b minus f of a over b minus a. So here, if I look at x squared on the interval from 0 to 2, x squared is continuous on that closed interval 0 to 2. I know x squared does not have any corners, cusps, vertical tangents, or discontinuities, so it is differentiable on the open interval from 0 to 2. So I am allowed to use the MVT, which says that somewhere f prime of c has to equal f of b minus f of a over b minus a. So what I do is I just start plugging things in here. Well, I don't know what c is, but I do know f prime of x is 2x. So if I plug c into that, I would get 2c. B is 2, so it's going to be f of 2 minus f of 0 over 2 minus 0. So I get 2c equals 4 minus 0 over 2 minus 0, which is just 2. So I get that c is 1. So at an x value of 1, on the interval from 0 to 2, the slope of the secant is equal to the slope of the tangent. Another type of question that we can use MVT on is one where it doesn't seem immediately obvious that I should be using MVT. Here we're told a car accelerates from 0 and takes 8 seconds to go 352 feet. Show that at some point during the acceleration the car had to be going exactly 44 feet per second. And so what it's asking us here is just not when is the car going exactly 44 feet per second, but that it just had to at some time. And that little tiny difference is the clue that maybe we are looking at MVT, or IVT, or EVT. It's one of the existence theorems. Well, because it's asking about an instantaneous rate of change, and the only information I have, I can find an average, this means we're going to be looking at MVT, because we want to show that the instantaneous rate of change at some point is equal to the average rate of change. So because we're using MVT, the first thing we have to do is show that we're allowed to use it. Well, a car accelerating, it can't suddenly be at one place and then skip to another without going everywhere in between, so it is continuous on that closed interval of 0 to 8 seconds. Again, velocity is the derivative of displacement, so velocity will always exist as it's accelerating. It can't skip velocities. So it is differentiable on that open interval from 0 to 8. And so we are allowed to use the MVT. So I don't know what my derivative is, but what I do know is that this is going to be my instantaneous velocity. But that should equal my average velocity. And average velocity is just displacement over time. Well, I know my displacement is 352 feet. I know the time is 8 seconds. And so when I do 352 divided by 8, I would get 44 feet per second. So according to the MVT then, there is a time, because the car's motion is continuous on the closed interval, differentiable in the open, there is a time in which it will be going exactly 44 feet per second.